Hello everyone. We have started chapter number 14 in the book of Elements of Chemical Reaction Engineering written by Fogler. This is chapter number 14 and this chapter is related to the mass transfer limitation in the reacting systems. The first lecture was about rate equation in the Cartesian coordinate system. The second lecture was related to the molar fluxes. We have discussed two types of fluxes. One was the diffusional fluxes. And the second fluxes was related to the bulk flow. So bulk flow fluxes and diffusional fluxes, and we have already discussed that the molar flow rate of component A in the z direction is equal to the concentration of component A into the volumetric flow rate of component A in the z direction. We have also discussed that the molar flow rate of component A in the z direction is equal to the molar flux of component A in the z direction and to the perpendicular area through which component A is transferring. So this is the perpendicular area. For z direction, the perpendicular area will be the x and y. So this is the cross-sectional area or the perpendicular area. This cross-sectional area for the z axis will be x, delta x and delta y. If you plot the Cartesian coordinate system, so if this is the x axis, then the perpendicular area to the x axis will this one. This whole area is the perpendicular to the x axis, and this whole area is this is the y direction, this is the y direction, and this is the z direction. So this is the delta x and this is the delta y. So this is the cross sectional or the perpendicular area, this one AC. So now we know that the molar flow rate of component A in the z direction is equal to the molar flux of component A in the z direction and the cross sectional area through which component A is passing. So the perpendicular area through which component A is passing, which is perpendicular to the x direction. So now we have already discussed this equation in the previous lecture. We also discussed that the molar flux of component A in the z direction are of two type. The molar flux of component A in the z direction can be diffusional flux of component A in the z direction. The flux of component A in the z direction can be diffusional flux, or it can be the flux resulting from the bulk flow. It can be convective flux. So it can be Ca into velocity of component A in the z direction. So the flux of component A in the z direction is equal to the diffusional flux of component A in the z direction plus the convective flux of component A in the z direction. So this is the diffusional term and this is the convective term. So I am writing here in, suppose this is a system, this is a 5, and suppose there are two components. One is component A, this is component A. These are the molecule of component A. The black one shows the molecule of component A, and the red one shows the molecule of component B. Molecule of component B. Now these are the component A molecule. The black shows component A and the red shows the component B. Now the component A, now the molar flux the molar flux of component A will be, suppose this is the z direction, this is the z direction, and this is a flow system entering, and this is the outlet. So the A will either diffuse, the A will diffuse in the molecule of component B. The molecule of component A will diffuse in the molecule of component B. So this is the molecule of component A. This is the diffusional flux. This is the diffusional flux JAZ, and this can be determined from the Fick's law of molecular diffusion. And if the component A and component B are flowing in the z direction with velocity uz, then the flux of component A in the z direction due to the velocity uz will be equal to Ca and multiply by uz. So this will be the flux due to bulk flow, flux of component A due to bulk flow of component A and component B. So if A and B are combined together, and if they are flowing inside the pipe or inside the system in the z direction, then there will be the velocity of component A, which is UA, there will be velocity of component B, there will be combined velocity, which is UZ. So in the flow in the z direction, the component A will also passes through perpendicular area in unit time, which is called the flux of component A, and which is denoted by Ca and multiplied by uz, this one. So the component A can either diffuse through component B by the by the diffusional flux phenomena, or the component A can either flow inside the system from left side to the right side in the z direction, which is called the flux due to bulk flow of component A and component B. The bulk flow term is nothing but when the component are flowing inside a system, then the flux of component A will be denoted by Ca multiplied by uz. We have already discussed this bulk flow and the diffusional flux in the previous lecture. So this is the diffusional flux, this is the flux due to bulk flow. Now we know that another color. So we know that the flux of component A in the z direction is equal to JAZ plus Ca into uz. But from the Fick's law of molecular diffusion, we know that this diffusional flux can further be written as JAZ is equal to minus DAB dCA, change in concentration in the z direction. So this can be, in place of JAZ we will write this term. We will write this term in place of this term, and this will be on its place. So now we can further simplify the above equation, which is WAZ is equal to JAZ, and in place of JAZ I am writing minus DAB dCA by dZ, and the convective term is this is the molar or the concentration gradient, the flux due to concentration gradient, and this is the flux due to flow. This is the convective flow. The flux due to flow or the flux due to convective flow will be written as, this will be Ca and uz. u is the overall velocity of component A and component B in the system. So this was component A, these are component B, the velocity of component A plus velocity of component B. Similarly, the velocity of component A multiplied by concentration of component A plus velocity of component B multiplied by concentration of component B will give us uz in the z direction. So this is the molar flux of component, this is the total flux of component A in the z direction. Now in the previous lecture we have derived a relation which was about the rate balance equation in a Cartesian coordinate system, and the relation was like that. So similarly, the flux, first of all I am writing the flux in the, this is the flux in z direction, the flux in the x direction will be like this one, minus dab dca, only the coordinate system will be changes. So here z, but here it is x, and this is the concentration of component A in the x direction, this will be x. Similarly, the flux, the molar flux of the flux of component A in the y direction will be minus dab dca in the y direction plus concentration of component A in the y, and the m2 the velocity of component and uy. So this is the these are the flux in z direction, x direction and y direction. So now in the previous lecture we have derived the rate balance equation in Cartesian coordinate system, and the balance was, and the equation was like that, it was like this type: d by dx wax minus d by dy way flux in the y direction minus d by dz flux in the z direction of component A plus the rate of disappearance or appearance of component A is equal to the change in concentration of component A with the passage of time. So this was, now in place of w, this was, suppose this is equation number x, this equation number x, and suppose this is equation number 1, this is equation number 2, equation number 3. So in place of wax, we will, which is this one, we will put this whole equation. In place of wx we will put this equation in this place. In place of way we will put this equation, we will put this equation in place of way, and in place of waz we will put this equation, we will put this equation in place of waz, and we will simplify it, further. So I am writing it, I am further simplifying this equation. So this is minus d by dx in place of wax. I am writing the flux of component A in the x direction is the combination of two fluxes, one is the diffusional fluxes and the second one is the convective fluxes, of the diffusional term and the convective term. And this is the title of this lecture, the diffusional and convective fluxes, also the diffusional and convective terms. So the wx is equal to minus dab, change in the concentration of component A in the x direction, plus ca and the ux, minus d by dy minus dab, change in the concentration of component A in the y direction, plus ca and the velocity of component A in the y direction, minus d by dz minus DAB, change in the concentration of component A in the Z direction plus the concentration of component A into the velocity of component A in the Z direction, bracket close, plus RA, this RA is equal to accumulation, which is change in the concentration with the passage of time. So at steady state this term will be 0. In the case of steady state, if concentration is not changing with the passage of time, this term will be 0. Now I am further simplify this equation. You can further simplify this minus plus the multiply by minus, it will be plus, and the DAB is constant. Suppose diffusivity of component A into the component B is constant, so it will be DAB and D square into CA dx square minus D by dx into CA into ux plus DAB D square CA dy square minus D by dy CA into uy plus DAB D square CA into dz square minus D by dz change CA into uz plus RA is equal to change in the concentration with the passage of time. At steady state this can be 0. Now these you can see these terms are, this term here DAB diffusivity is given, in this term the diffusivity is given, in this term the diffusivity is given. So I am combining these three terms, this and this. I am combining these three terms and I will take the DAB common from these terms. So the DAB DCA x square DAB square CA y square plus DAB CA by dz square, and the other term will be written as such minus D by dx CA into ux minus D by dy CA into uy minus D by dz into CA into uz and plus RA is equal to change in concentration with the passage of time. So actually this velocity in the x direction, this ux, this uy and this uz is constant in the problem, so it will come out from the differential, and this the final equation will be look like this. So DAB by x square DAB CN dy y square DAB CN the z ux uy and z are constant, so ux dca by dx uy dca by dy minus uz dca by dz plus RA is equal to dca by dt. So at steady state this term will be 0. If the component is flowing only in the z direction, then this term will be 0, this term will be 0, only this term will come, ux will be 0, uy will be 0, because component is only in the z direction. So this term and this term will occur, and this will be also occur, and at steady state this term is also 0. So we will get the second order partial differential equation. So second order partial differential equation, we will get second order partial differential equation. So this is the second order partial differential equation. You can see this is the second order partial differential equation. We can further simplify this equation by using the boundary condition. So if the flow is only in the z direction, then this equation, this whole equation will be written as dAB CA by dz square and uz dCA dz plus RA and dCA by dt. So at steady state this will be 0, and we will this term will whole term will be equal to 0. So this equation is called the second order differential equation, which can further simplify by using the boundary condition. So in the coming lecture we will use the boundary condition to solve this equation. Thank you very much for your attention.